We've already seen that the electric field oscillates in a plane perpendicular to the direction of its travel. So if we imagine light coming out of the screen at you right now, the possible polarizations are infinite. It's every possible angle around a circle, just like all these different colors here. Each one could represent a possible polarization, a direction for the electric field to oscillate for the light coming out of the screen. The way we investigate the polarization is to use a polarizer. The most common form of this is a sheet of plastic made of long chains of polymers called a Polaroid filter. Light with the polarization direction along the molecular chains actually gets absorbed, and light oscillating perpendicular to the chains gets transmitted, but the way we draw it, we'll draw it with lines indicating the direction of light that's allowed to get through instead of really the chains. The part that's a little bit weird about this is that light doesn't have to be polarized in exactly the right plane to be transmitted by the polarizer. There's a chance for light polarized in any direction except exactly perpendicular to make it through the polarizer. One common analogy for this is to imagine the polarizer being like this curtain of beads here, and you're trying to walk through it carrying a meter stick. If the meter stick is vertical, it should be very easy for it to get through, and if the stick is horizontal, it should have no chance to get through easily. So the important thing is really the projection of the stick in the direction of the polarizer here. We already know how to find the projection of a vector in some direction, and it's just the cosine of the angle between the vector and whatever direction we care about. We know that the intensity of light depends on the square of the E field, so if we put these two ideas together, we get what's called Malice's law, which says that the intensity of light coming out of a polarizer is equal to the intensity that went in times cosine squared of the angle between the initial polarization and the direction of the polarizer. So if we have light that's vertically polarized, send it through a polarizer in the same orientation, theta equals 0, cosine theta equals 1, and we should get the initial intensity back just like we hadn't run it through a polarizer at all. Now, in real life, they're not quite this perfect, and they'll absorb a little bit of light no matter what. Just like the cleanest window you've ever seen, you can still see it there because it's reflecting some light. This is what this kind of problem would look like on a test. I'd draw some sort of incoming light, the lines showing the direction of the polarizer, an arrow at an angle showing you, or at least the angle, showing you which way the polarizer is angled, and then the light coming out. Now, a slightly different problem. What if the incoming light's still vertically polarized, but now the polarizer is 75 degrees to the vertical? So now we have a much smaller chance of the light getting through because it's almost, if we move this 15 more degrees, it would block all of it. So we don't expect much of the light to get through. We put in the numbers for Malice's law, and we get cosine squared of 75 degrees is about 0.067. So this means less than 7% of the light that was initially vertically polarized gets through here. Now, whatever does come out is polarized at this exact direction, at 75 degrees to the vertical. Most of the light that you see every day is unpolarized, and what that really means is a random mixture of polarizations. If I want to indicate unpolarized light on a test, I'll draw something like this. So you've got all sorts of different polarizations here. If we have unpolarized light, what the math from quantum mechanics tells us is half of it will get through and half of it won't, whatever the polarizer angle. So I don't have to know what this theta is at all. If I know I have unpolarized light going in, I'll get half the intensity coming out, and it will be aligned with this polarizer. So now what would we get if we did this? We have light that's unpolarized. It goes through this polarizer 30 degrees to the vertical, and then through this one that's 40 degrees to the horizontal. So we already know half of it gets through the first one, right? Because we know unpolarized through any polarizer, half of it gets through. Now this light is 30 degrees from the vertical, and what we really need to know is how far away is it from this this final polarizer? What's the angle between the two polarizers, essentially? So if the final one is 40 degrees above the horizontal, I could also say it's 50 degrees from the vertical. That's the same thing. So if it's 50 degrees this way from the vertical, and this one is 30 degrees the other way from the vertical, that means the net angle between them is 80 degrees. So the light that gets through both polarizers will be half of the original times cosine squared of 80. That's only about 1.5%. Now, what if we use unpolarized light and we send it through crossed polarizers? So this one is horizontal, this one's vertical. We know half of it gets through the first one, but it's then polarized horizontally. If we have horizontally polarized light hitting a vertical polarizer, that angle theta is 90, cosine 90 is 0, and we get nothing coming through. So now we could say we have essentially a perfect device for blocking light. What about if we have this sort of two fences that make a perfect barrier? What if we put a third fence in the middle? It seems like that, won't do anything or would only make it better if possible. But what happens is 50% of the light gets through the first one. Then this horizontal light hits this light that's 45 degrees to the horizontal and to the vertical. Half of it gets through there because cosine of 45 is 1 over square root of 2. We square it, we get half. Then this light that's polarized 45 degrees to the vertical goes through a vertical polarizer. Again, cosine squared of 45 is 1/2. We get half of that out. So with just the first and last polarizer, we'd block all the light. But when we add this one in the middle, that's the intermediate polarization angle between the two, we get 1/8 of the light. So it's a little surprising generally, but the thing you have to remember is all the light knows about is what is its polarization right now. That's what determines its chance of getting through the next polarizer. There's another interesting effect that we use in making sunglasses, and it's called polarization by reflection. To see this, we go back to the idea of incident light, reflected, and refracted light that we saw when we first started talking about index of refraction. So we've got an unpolarized light beam coming in from the left, and what that means is we've got light with arrows in all directions here, going all around this. Not in the direction it's traveling, though. It's not allowed to do that. But all these other directions, kind of like, I don't know, a spinning baton or something. We can break that down into a component out of the page, the green part, and a component parallel to the page, the red part. So these things hit the surface of this non-metallic screen here. Hits the surface. Some of it goes in, some of it's refracted, some of it's reflected. This is nothing we don't expect. However, what we notice is if you look at the orientation of this polarization vector, it would be going in the direction of travel. If the red arrow made it through the reflection process, the red arrow would be in the direction of travel, and light is not allowed to oscillate like that. So we lose that polarization. That one has to go entirely into the refractive medium. It has to go entirely into the water or whatever we're looking at here. So what this means is just because it got reflected, the light ends up polarized. We now only have this component. We've lost this one. What that will let us do is block this polarization if we want. If we have our polarizer oriented up and down, it'll block this polarization of light. What this means is it will get rid of glare for us, because when this light bounces off water, that's what we call it. It's glare. We could easily design a smoked filter that blocks half of the light, and that's what a polarizing pair of sunglasses will do. They'll block half the sunlight. But if we have them polarized, we don't just block half of the glare, we block all of it. Now, to find the angle where this works best, this is called Brewster's angle, and what we would use is tangent of Brewster's angle is the ratio of these indices of refraction. The way you can work this out, or you can look in the book, we know that if we have a 90-degree angle here, that's what's going to do it. And the way we would have a 90-degree angle, we'd have to look at our angle of incidence and our two refractive media to see, exactly what angle do we have to go in for that to happen. This is how we'd solve for it. So this is why we do polarized sunglasses. And to see a comparison of what it looks like when you do it, if you don't have a polarizer and you look at the surface of water, you see what's here on the left. If you do have a polarizer and you can get rid of the glare, you can see right into the water. And the same thing happens with cars. If you don't have the polarizing filter, you get this picture on the bottom where it's hard to see in the car. If you do have it, it looks like the windshield disappears. So the ability to remove glare with the polarizer is actually a pretty useful trick if you're making glasses.